Welcome to Unitronics webinar on UniCAN. It is the 20th of April, 2011. My name is Anthony Nicolaitis here in Unitronics US Tech Support. I have Jason Lettieri here as well, who is going to be answering questions if you type them as we go along. Today we'll be going over the Unitronics UniCAN protocol. UniCAN is a CANBus protocol. We will go over a quick slideshow, and we'll look at an example of two controllers communicating, and then we'll look at an example of our EXRC1 remote expansion adapter communicating to a 570 with a IO DI8 R08 and an IO AI4 AO2 sending remote IO back and forth between the controller. Okay, so to get started, again, welcome. Unitronics CANBus communication. We're going to go through this quick slideshow. First off, CANBus is a physical layer, meaning it is the cable and the network that we communicate over. We have the ability of connecting up to 63 controllers and a PC, or 64 devices, controllers on the CANBus network. We're going to take a look at two protocols we offer, but first off, here is a wiring diagram of the CANBus network. You see it is a, sorry, like RS-485, it is a daisy chain topology. We have controllers connected. We have it's a 24-volt power bus. We do need to include a 24-volt power supply. Each of the end controllers needs to have a 120 ohm terminating resistor. We can see on this chart the baud rates that are capable on these, the baud rates we're capable of on this network. 25 meters and below, capable of 1 megabit a second. 100 meters and below, 500 kilobits. 250 meters and below, 250 kilobits. You'll see that we can have about a kilometer of CANBus network. And again, this is specific to CANBus, not Unitronics. We take a look at the cable. We require, not recommend, shielded thick cable. You see there's a pair, red and black for power, and a pair for data, the blue and white. We also have a shield. So this is a five wire cable, I should say. Unitronics protocols we offer. First off, we have the CANBus ISC, which is the inter-slave connection. This protocol was developed. I'm sorry, can you hear me? Can everyone else hear me? Yes. Okay. Maybe, Paul, need to turn up your volume a little bit. It seems like everyone else can hear. Okay. Thank you. Sorry about that. Okay, so Unitronics protocols we offer. First off, we have the CANBus ISC, which is the inter-slave connection. This was developed for the M91 series and U90 ladder. This is our first proprietary CAN protocol. It was very good at its time. There's a couple limitations. Really, this protocol is good for sharing information between 8 controllers at a time. Again, we can have up to 64 controllers on the network, but only 8 can talk to each other. Using this protocol, we need to include a layered topology where 7 controllers will talk to one master, and then those, if we gather 7 masters, they can talk to another master. We can build a hierarchy with this, but it wasn't the most efficient at sharing data with all the controllers. So with VisiLogic and later developments, we developed the UniCAN protocol. And UniCAN is really the best way we have of sharing information between Unitronics controllers. We can have up to 60 devices on the UniCAN network, and we'll see that this includes controllers and remote I/O. In addition to our UniCAN and ISC protocols, we offer third-party protocols. CANopen is a very popular and widely used CAN protocol. We offer a CANBus Layer 2, which you can think of in terms of our ASCII protocol function block. This is an undefined CAN protocol we have also the ability to parse out messages and pull information from the messages and build also packets to send out on the CAN bus. So if we have an undefined CAN, we can work with it. In addition, with the enhanced controllers, we've added the J1939 automotive CAN bus protocol. This is for talking to automotive vehicles like the ECU in trains and automotive networks. CANBus network to PC. With UniCAN, we have the ability to bridge a network using an RS-232 cable to the PC. So if we have a controller running VisiLogic, we can connect to the RS-232 port of a single controller on the CANBus network, and we can communicate to all of the controllers, meaning we can download programs, or we can make changes, or we can view live with any of our software that supports network communication. So VisiLogic, remote operator, remote access, data export, all these communications are available over the CANBus network. So in terms of communication, this is one big advantage of the UniCAN protocol. As I mentioned earlier, we have the ISC, the inter-slave connection. This protocol can share 16 system bits and 16 inputs and 2 system integers over the network. We can communicate, again, to 7 other controllers, so we can share information not with everyone, but with certain controllers on the network. We're not going to focus on the ISC, but it's important to know it's available. The M90 models only support the ISC. The Vision controllers support UniCAN plus the ISC. So if we need to create a network where we talk to the M90 controllers, we can use the ISC protocol, or we can use Modbus over RS-232 or 485. Oops, going the wrong way. Now to our UniCAN protocol. UniCAN is a multi-master protocol. Again, we support up to 60 devices on the network. Multi-master means that each controller has the capability of sending to any other controller that is on the network. If I have controller 1 and I want to send messages to controller 5, I can do that. As well, if I want to send messages from controller 3 to 5, we can do that. It's not a master-slave protocol, as you might be familiar with Modbus. There's no asking for messages, there's simply sending. We can create a lot of different structures with this that we'll see. UniCAN, as I mentioned, is the best way to share information across the Unitronics network. We can send up to 32 messages in a scan. Each message contains 16 memory integers, and we can have the capability of sending 16 high priority and 16 low priority messages. So that would be 32 messages or 512 memory integers in a single program scan. So again, there's a lot of potential available with the UniCAN protocol. And we'll briefly take a look at the functions we have available with UniCAN. The first one is the CANBus setup. We'll take a look at all these in application, but quickly, under our COM initialization, you notice we have to select UniCAN, and we have to select a baud rate. So we're going to be using 250 kilobits. Again, that's good for up to 25 meters. Also, we have to assign a unit ID number. So the unit ID number is the way we're going to address each specific controller. Again, it's going to be between 1 and 60. Okay. So our first UniCAN function block is the send registers function block. Using this, we can send a message to any controller. We can send up to 16 memory integers, and we can set the priority as high or low. And we'll take a look at what all these ladder-specific functions are in an application. We also have the capability of broadcasting a message to every controller on the network. Specifically, we can broadcast a bit and a memory integer to each controller. The broadcast function block we select the memory bit and the memory integer we'd like to send, and in every controller we'll receive the bit and system bit 200, the memory integer and system bit 200, system integer 200, and the network address of the controller that sent it in system integer 201. Again, this is how we can share information to every controller at the same time. We also have a check alive function. What the check alive function does is check to see that each controller is available on the network. Each controller will broadcast a check alive packet every half second. What the function block will do is listen to a specific controller's check alive. We can use this to create a timer function. In the example here, the timer is set for 2 seconds. So if we miss 4 check alives, we'll know that the controller is not available on the network, and we can do something, whether it's alert an alarm or simply not send information to that controller and route it somewhere else. We also have a message arrive function. The input for this is the controller that we're interested in seeing a message come from. When we receive a message from this controller, the linked memory bit will go high for a single scan. Using this, we will know if we received a message from controller 5 or controller 6, and we can route the information to the appropriate register depending on which controller we sent it from. One interesting piece of information we have available as well is system integers 240 to 243. They offer a bitmap of each specific controller, and the bit for the appropriate controller will be high for a single scan as well. Okay. So that's in a quick overview of the UniCAN protocol. We're going to look at some specific examples. Again, first we're going to look at communication between 2 controllers. Okay. I'm going to exit here. And I'm going to look at VisiLogic. And I have an application set up on 2 570 controllers, and I'll show you the online view. Give me 1 second to get this set up. So what we see here is the HMI view of both of our controllers. We can see we have a couple of pieces of information. First off, communication okay. We'll take a look at this one in a second, but let's look at how we send a packet or send a piece of information. So on the unit 1, I'm going to change the values to 1, 2, 3, and also 2, 3, 4. And we'll hit the send button, and we expect these values to show up in the received from unit 1. And they do. And we notice we have also a message arrived. We can do the same for unit 2. We'll send 4, 3, 2, and 3, 2, 1. Oops. That's okay. And notice the information shows up here, and we have a message arrived. Now if I unplug the CANBus cable from one of these controllers, we notice we have a message that states error with COM error with unit 1 and COM error with unit 2. When I plug the controller back up, the communication is okay. Okay, so these are a couple little functions that we're going to look at in the ladder now. I'm going to close these online views, and I'm going to bring up the application for CAN 1, and then we'll compare the similarities to the Unit 2 program. Okay, so in Net 1, again, whenever we have communication, we use our SB2 power-up bit. The first thing we have to do is initialize the COM port, and then we set up a protocol. So with UniCAN, it's a little simpler. All we have to do in the COM initialization is select UniCAN from our drop-down list and select the baud rate. Now while we're here, it's worth mentioning the COM initialization, if we're familiar with our RS-232 and 485, is where we select our COM 1, 2, or 3. Again, if we're using our CANBus ISC, if we want to talk to an M90 series controller, we'll select that here. We have our UniCAN protocol. In addition, our CAN Open and CAN Layer 2. And for enhanced controllers, we can run multiple protocols at the same time. Specifically, we can run CAN Open and UniCAN. CAN Open and CAN Layer 2, or CAN Open and CAN, J1939. One other option we have is CAN layer 2 scan only. We can use this if we simply want to just read all of the packets that are coming in over the CANBus network. We're going to select UniCAN today and hit OK. And the next piece of information we need to set is the PLC network ID. The input for this is just a list of network IDs. So my controller 1 is going to be CANBus ID 1, and my controller 2 is going to be CANBus ID 2. If we want to know where to select these from, the COM drop-down, COM port and initialize is available here. And our UniCAN function blocks are available here. Okay. We've also included the PLC name in case we need to address this with a piece of software that requires a PLC name, such as VisiLogic. Okay. So our first function block we're going to use is the UniCAN check-alive function block. As I mentioned, our controller 2 is network ID 2, so we've selected for this function block an input of unit 2, and we can see, again, we can select any of the controllers available on our UniCAN network. And our output is going to be MB0. So what we should see every half second is that MB0 will go high for a single scan. Now we're using this with a timer network. TD0 is a 2-second timer, and we'll go online and just look at this real quick. What we should see is that every half second, TD2 gets reset. And let's bring up TD2. It's on my other monitor. We see the countdown go from 2, and it never quite reaches 1.5 seconds. Okay. If I remove the cable, we'll see the countdown gets to 0. And now below we activate MB1, which is our status message on the HMI. So we're now displaying COM error with unit 1 on the HMI. If I plug the cable back up, since it's a TD type timer, we reset the timer, MB1 goes low again, and we can continue communication. So this is simply the check alive function block. Okay. The next function we're going to look at is the UniCAN send. Now, MB3 is the button on the HMI, the send button. You'll notice the structure from all of our communication protocols, Modbus, if we looked at that protocol. We're going to set MB5. MB5 is our send value request. MB5 will be set and stay high until we perform this network and reset MB5. Now, why do we do that? We do that because in the case of network traffic, a situation where we can't send a message, we don't simply want this message request to go away. We want it to wait for the next available opportunity to send a message. And you'll notice that the UniCAN send function block has 2 other function blocks for it. First off, we have system bit 201. This is telling us that the high priority message buffer is full and we have to wait to send a message to it. So we use this contact to ensure that we can pass information through to the buffer. The second is a compare statement. So we're comparing MI0 to 0. Now what is MI0? If we pull up with F1 the help file for UniCAN, and we go to our UniCAN help file page, we can click on send registers, and we can look at the status messages for this function block. We see we're comparing to 0. 0 means the previous message was successfully sent. This is good. This means we don't have a problem. But notice that if we're not 0, we have some situation that's going to require us to wait till the message is 0. Status 1, message ready to be sent, but network is currently busy. 2, destination ID number is greater than 60. So it's giving us some information that says there's a problem. We can't send a message, and you should probably take a look at the status message and figure out what the problem is. So we'll close this. Well, maybe we'll keep it in the background. Where did that MI0 come from? In our send function block, we'll notice that one of the parameters, the out parameter, is the status. So we first have to create our UniCAN send function block, and then we can link the status to the compare to 0. Other parameters in the UniCAN send. Well, first off is the destination ID. So again, we have 2 controllers. We are ID 1, and we want to send to controller 2. So we're going to select 2. group ID number, we just leave this as 0. It doesn't affect our UniCAN communication, but it's a parameter for CANBus messaging. We're going to leave it as 0. Now, the source start address, in this case MI10, remember we're sending memory integer 10 to controller 2, where we're sending 10 and 11, but we'll take a look at that in a second. So again, MI10, our source address, this is the address in our master controller that's sending to our slave controller. The source vector offset, we could use the offset if we wanted to offset based on MI10, meaning if I selected the value of 1 here, we would send MI11. If I selected the value of 2, we would send MI12. This can be useful for indirect addressing. If we want to create a scheme that's going to send MI10 and 11 and 12 and then 13, we can use this in that manner. Also, if we simply have different local addresses for information, we can just jump between them using the offset. Now, what we see is the description source start address. Actually, this is the destination start address because we've already given it a description as MI10, and we're sending to our other controllers MI10. We can't have 2 different descriptions for MI10. But if I just click the next get unused, you notice the description is destination start address. This is the address that we're sending to in our other controller, our controller 2. I'm not going to change it from 10. We see below, again, the destination vector offset. So again, if we set it as 2, we would send MI10 to MI12 in our controller 2. Okay. And now below this, we have the length. And again, I mentioned we can send 16 memory integers with a single send message. This is where we select this piece of information. We're sending memory integer 10 and 11, so we've selected a length of 2. If we wanted to send 16 memory integers, we can select 16. But it's important to note that this is a vector operand, and what we select as the source start address is the start of the vector. So we can send between 1 and 16 integers in the vector starting at the start address. In the priority, we can select either high or low. In this case, we've selected high. What the priority does is send the message to either the high or low priority buffer. And the buffer can contain, each buffer can contain 16 messages. So we can have 16 messages in the high and 16 in the low. All of the high priority messages are sent before the low priority messages. Okay, so this is our send command. If we look at the next function block, it's the UniCAN message arrived. And we'll notice 2 parameters here. First is the controller we're interested in receiving a message from. So in this case, it's CANBus ID 2. And the output is a memory bit that's going to go high. So when we receive a message from ID 2, MB2 will go high for a single scan. So we can go ahead and we'll go online and take a look at this. I'm just going to send a message from controller 2. We want to see this bit goes high, and it does. And we notice what it's doing is activating a 3-second timer. After 3 seconds, it resets itself. And this is a message arrived binary text message we have on the HMI. So whenever we receive a message from ID 2, MB4 will be set. MB4 is a display variable, so we'll display the message arrived. And with our timer 1, after 3 seconds, we're going to reset the message. So it's a simple way to notify us that we've received a message. In a real situation, we can use this information. The message arrives, and we can either copy the information to the appropriate registers, or we can perform some function. So again, these are the tools available, and it's up to the user to decide how they want to use them. But these are very, very useful pieces of information here. Okay. So we should now take a look at the Unit ID 2 application. Give me a second just to arrange these windows so we can see this in a useful manner. So as we noticed from the HMI, the programs are very similar, actually pretty much identical, with the exception of a couple things. So what can we expect to be different here? Well, the first off, of course, is the unit ID number. Sorry, give me one more second here. Okay. So in net 1 of controller 2, again, we have our UniCAN initialization. These need to be the same so we can communicate with each other. That means the baud rate needs to be the same. And in program 1, we had ID 1. Program 2, we have ID 2. Okay. PLC name for program 1 was PLC name 1. PLC name is PLC 2. Okay. So that being said, everywhere we have a function with an ID number, we should match the opposite one. So again, we had unit ID 2 for the check alive. Now we have unit ID 1 for the check alive. Okay. The timer network is the same. If we continue down to the send command, we'll see that these networks are set up the same as far as the send goes. But the unit ID, destination ID, is different. Okay. And the information in the check alive, the message arrived, is also different. Okay, so very similar programs. The only difference is the network ID, so we can communicate to the appropriate controller. Okay, I'm going to close these out now, and we're going to take a look at the EXRC1 example. Just give me 1 second to arrange these, and then download them to the appropriate controllers. Close this one down quickly, and we'll talk about the EXRC1 and the 570 communicating with each other. So let's look at this application for CANBus master. I'm going to go online with this, and we'll take a look again at the HMI, and we'll see what's going on here. All right, got to plug up that one. Okay, so here is the HMI. Let's put this over here, of the controller. We notice there's a couple things. First off, communication okay. Second off, we have a set of inputs and an analog input. And we have a set of outputs. What you can't see I have in front of me is my 570 connected to an EXRC1, again, the remote expansion module adapter, connected to a DA8 R08, which is an 8 digital in and an 8 relay out module, and then connected to an AI4 AO2, which is a 4 analog input and 2 analog output module. I can control the relay outputs on these modules if I select these buttons here. So as I click them, I'm turning the relays on, and I click them again, I turn them off. It's a simple toggle. If I had the inputs wired up, I could turn them on, and we would see here that they would go high. And I have a 5 volt, about 5 volt analog input on the analog input side of the AI4 AO2. And that's what we see here. So, again, if I remove the cable, we should see communication okay. Turns to COM error unit 2. We don't have communication to unit 2. And the analog input's gone down to 0 volts. We don't want to get a false reading, basically. So we also turn off all of the digital and analog outputs connected to the EXRC1. We don't want this I/O to go out of control, basically. We don't want anything on that we can't turn off under some control. So everything turns off on the EXRC1, and we need to make sure that the messages sent from the EXRC1 are also 0 to the 570. Okay, so I'll plug this back up. The relays are back to the state they were when we unplugged the cable, and we received the latest value from the analog input, which again is just a solid 5 volts. Okay, so I'm going to close this. We'll take a look at the application for the 570 first, and then we'll look at the EXRC1 application. So if I go to main module, you notice we have 2 subroutines in the main. Click on main first. And so exactly what we should expect to see if we're doing communication. System bit 2 is a power-up bit. PLC network ID, in this case the 570 is ID 1. And our COM initialization for UniCAN. Okay, again, 500 kilobits, UniCAN. Okay. Now, our second function block is a check alive function block. This is checking to see that we have communication with the EXRC1. Every half second we should get a message from ID 2, and we'll pulse MB 4002 high for a scan. And this time we're running a 1.1 second timer. Okay, we'll see that after we miss 3 reads now, we'll go high. Okay, so I'll plug this back up. Now, this example we're looking at is the standard program that comes with the EXRC1, and I made a slight modification to both to include an analog input value. So, along with displaying the message, no communication, we're going to store 0 in the MI4. We'll talk about that after we talk about the EXRC1. But basically, this is the register we're receiving the analog input to. If I don't receive I/O communication, I want to store a 0 here to signify. So, let's take a look at the output side first. You'll notice in this subroutine, we'll start by taking a look at net 7 and just explain what's going on. MB0 through 7, these are the buttons we had on the HMI. They're going to toggle outputs 160 to 167. This is just so we have some example data. Okay, and in our system we actually can work with outputs 160 to 167 and link them to the output on the EXRC1. Okay, so again, our information on our outputs is output 160 to 167. Take a look at the top of the program now. There's a couple things going on, so to talk about this linearly is not going to make too much sense, but after we take a look at all the functions, I think it'll be a little more clear. So first off, we're doing a compare. MI1799 compared to 0. What is MI1799? Well, we see the description status. We know that we're working with the status for the send, but if we want to see, we can right-click find MI1799, and we'll bring up in our display in the bottom, of course, net 1 is the one we searched for, and we see net 6 as well. Unitronics can send. Net 6, our UniCAN send. We see the status messages from this UniCAN send block. Okay, I only point out this find feature because it's very helpful to deconstruct a program that we haven't seen before. Okay, so we're comparing the status message to 0. We're seeing if there's a message waiting to be sent. If there's no message waiting to be sent, we're going to drive MB 4011 high. In net 2, if 4011 is high, we're going to run this struct command. Now we haven't talked about this. We can find under vector struct here. And let's take a look at what it does. Now, if you noticed, the only values, the only registers that we were able to select with the UniCAN send function block was memory integers. Now this might seem like a limitation at first. You say, what about my system bits, my system longs, double words, memory floats, every other type of operand I have available to send? Well, the UniCAN send function block is designed to send memory integers, and this way it can send things efficiently. What we can do is package our mixed data types into a memory integer vector, and that's exactly what the struct function block does. You notice that we have a parameter here, copy data direction. We've got 2 options, from vector to mixed data locations, and from mixed data locations to vector, what we're going to do is take mixed data locations and we're going to create a vector from these. So you notice below, outputs 160 with a length of 8. This was our 8 buttons on the HMI, or what was linked to the 8 outputs, 160 to 167. What we do here is link the start operand, and we give it a length, and it will calculate the byte size. Okay, so this whole message, 8 bits, is 1 total byte. And that should make sense. If we add here 1 memory integer, I'll just select the next available, and I say 1, we should see it's 2 bytes. And that should make sense. Memory integer is a 2-byte operand. Okay, I'm going to just get rid of this one. I don't want to change anything. Notice after you make a change as well, you can hit compile before you can hit OK. Just going to make sure that the vector you're trying to calculate makes sense. Anyway, we're going to save this to MI 1800. If it was mixed data up to 16 memory integers long, we would save to MI 1800 through 1815. Okay, and this is how we're going to enable us to create packages to send with our send command. Okay. Alternatively, the from vector to mixed data locations, because we package this in such a way, on the receiving side we need to give the same scheme of operands and lengths, and we'll go from a single memory integer vector to all our mixed data types. So we can save outputs to the outputs, we can save bits to memory bits, longs to longs. We just need to make sure we define these structures the same. Otherwise, we're not going to be able to read them outright. It's basically just parsing the information and putting it in the correct places. Okay. So that being said, the important part here is outputs 160 to 167 are being stored in memory integer 1800. Now, because it's only 8 bits or 1 byte, we're only going to do operations, compare operations for a single memory integer. So in the next function, we see if MB4011 is still high, we're going to compare memory integer 1800 to 1810. If they're not the same, MB4010 is going to go high. Now, what does this mean? We're comparing the vector we just created to a vector called buffer. Now, where does this buffer come from? In the net below, we're going to see that we copy 1800 to 1810. What we're doing here is creating a buffer of this scan's output table. We go around the scan, we come back in, we create a new struct into 1800, and we compare. If there was a change from the last scan to this scan, we know we've had a change in our outputs. So we've updated the output table. Now, what this is doing, again, is letting us know between scans if there was any change to the data we've put into the struct. In this case, if any of these outputs change, we should expect that MB4010 should go high. Okay? So we're going to use this information to determine when we send a message. If we look at nets 5 and 6, we'll see that if 4011 is high and there was no changes, we're going to run a timer, a 100 millisecond timer, and the output of this timer is to run our send command. Alternately, if there is a change, MB4010 will go high, and in net 6 it's going to run the send command. So the two stipulations we have here, either there was a change to that output table or 100 milliseconds has passed. We send the information to the EXRC1. Okay? All right. So the next thing to look at is the EXRC1 program. We'll take a look at how it handles information coming into it. So I'm going to close this one. And I'm going to open the EXRC1 program. Again, the CAN master for EXRC1 and the EXRC1, these are the default programs we give as examples, and the default program that comes in the EXRC1. Let's take a look at now the input side. I'm sorry, we're still looking at the output side. Okay. So what we should expect to see anytime we're trying to get information specifically from a controller or a device, message arrived from Unit 1. This is telling us that the 570 has sent us a message. MB3660 is going to go high. When MB3660 is high, we're going to run the struct command, but notice this time it's in extract. So let's take a look at this. We're going from 1990. This is the address we sent the information to. And we're going from vector to mixed data locations. And we notice that the first is output 32. Okay? Now, this is set up a little differently than we saw in the previous. The default application for the EXRC1 is designed to handle, by default, 8 digital input-output modules. So if we have many DI8s, or we have TO16s, the 16 transistor output, or RO16s, the 16 relay outputs, by default we're set up to handle communication to them. We see that we link to outputs 32, 48, 64, 80. This should make sense that we can do this by default, because if there is no output on the 570 side, all we're going to send is zeros. And if we're sending zeros to outputs, well, it doesn't really matter. So it's kind of a trick we're able to take advantage of to set up a program by default that's going to work with digital modules. Now, the modification we made to this program, we'll take a look at in a minute, is to add an analog input value. But again, by default, this is set up for digital modules. So the message comes in, and the output goes to output 32 with a length of 16. Of course, we had only 8 bits, so we're going to update outputs 32, 33, 34, 35, 36, 37, 38, 39, whichever of those bits was high. Okay. Again, this is how we receive and put the information into the correct place. Now, the other portion of this is the check alive. And again, we're going to run the check alive for ID 1. If we don't have a check alive for 1.1 second, we're going to come down, and SB3 is a 1 second pulse. So every 1 second we haven't, we're going to drive MB4090 high. Now we have a couple special system bits for the EXRC1. System bit 252 is the LED on the EXRC1, which is going to blink when we don't have communication. And system bit 254 is the system bit that turns off all of the outputs and inputs. I'm sorry, it's not going to turn off the inputs, but turns off all the outputs that are linked to the EXRC1 and writes them all to 0. Okay. So if we don't have communication from the master controller we're interested in, we're going to turn all the outputs off. So let's go online and we'll take a look at this one. Okay, first off, system bit 252 is high. That means the light is solid here. So let's unplug this. We can see we're now blinking, and our buscom light is blinking, and system bit 254 is high, and our I/O has gone to 0. Okay. When we connect the communication again, we take the negative transition and we reset 254. Okay. And the output should go back to the state they were in previously. My output 0, 1, 2, and 3 are still high. Okay, so we saw how we received a message. Let's take a look at the hardware configuration of the EXRC1. We see first off, under Remote I/O, we have the option for EXRC1. If we're used to using Expansion I/O, we'll see those here. And this is what we can use paired with the EXRC1. So we have on our defined hardware configuration, EXRC1, we've set our I/O DI8 TO8 is our first module. Again, outputs 32 to 39. We should see vector copy. This is the information that's being written to by that extract command. And then we have an analog module, which we've defined one analog input on MI4, a 0 to 10 volt, and an analog output also 0 to 10 on MI3. Now I've given this a startup value of 2056. This is a 12 volt, so the values are 0 to 4095. 2056 means we're putting 5 volts out on that analog output. And we're reading it back in. I have a wire connecting the two to MI4. And this is just to give us some example data. Okay. So let's take a look at the input side. And what we should see here is something very similar to the send commands that we just saw on the 570, except now, again, we were working on the 570 with a single memory integer. We're going to work with an entire vector of struct information. So again, MI2040 CANBus send status message. We're going to compare it to 0. If it's 0, there's nothing waiting and we can send messages. MB4092 is going to go high. We're going to run our struct command. This time, we're taking all of the available digital inputs and we're building them into a vector. So this again assumes that we can have 8 DI16s connected to this module. And even if we don't have 8 DI16s, the values are 0. And if the values are 0, they don't matter. So again, by default, this is set up to work with digital input and output modules. Now we're building this from mixed data locations. We're going to save it to MI2000. Okay, and you should notice we have total bytes is 16. Okay, so we're collecting all of these into 8 memory integers. MI2000, 2001, 2, 3, 4, 5, 6, and 7. Now again, what we saw in the previous example was a single memory integer. So we did a store command, and then we did a single integer compare. In this example, we're going to use a vector compare. So under vector, we see compare, and we see copy. Just like we did before, we're going to compare MI2000 to 2010. What is 2010? Well, in the next net we see vector copy of 2000 to 2010. So again, we're going to do a struct. We're going to build 2000. We're going to compare it to the previous scans, 2000, which is 2010. And we're going to see if there were any differences. The output here, MB4091, if it's 0 or low, there's no change. I'm sorry, if it's low, there's a change, and if it's high, there's no change. Okay, so our output now, 4091. And just like we did before, if 4091 is high, we're going to perform a send command. Or if 100 milliseconds have passed, we're going to perform a send command. Okay. Again, we compare to 0 for our status message. We are using our system bit to determine if the buffer is full. And we have our first send command. This is MI2000. We're sending to MI2000 in our controller. We're sending to ID number 1. And this time we're sending with a length of 8. Remember, we built a vector with a length of 8. And the status, the priority is high. Because it's I/O, we're going to call the priority high all the time. We want to make sure this information can get across the network. Okay. And we've added one more send command here, just to illustrate another send. We're sending MI4, which is the analog input that's connected to the EXRC1, and we're sending it to MI4 on the 570. Okay, again, ID 1, vector offsets are 0, the length this time is one single memory integer, and the priority is high. We left this based on the sends of the previous. It's a memory integer for an analog input, so the update time is, if we have a few especially, is going to be on average longer than 30 milliseconds. So in this case, it's okay to just use 100 millisecond or the change of the digital inputs to send the message. Okay. Oh, we don't have to worry about those. Okay, so that's the send from the EXRC1. If we want to close this down again, we can take a look at the receive on the 570. And now let's take a look at the input side. And we can see very simply we have message received from unit 2. MB 4012 will go high. If 4012 was high, we'll go into run the mixed the struct to pull information from the vector to mixed data locations. Now again, we're only concerned with, in this example, 8 bits, so that's one single byte. We're going to take the information from the previous inputs. It's going to send it again to 2008. When it's received, we're going to store this into 2160. And this is the inputs that are displayed on the HMI. Okay. And the other piece of information, MI4, if we look at the HMI, will be received in MI4, and we've linearized it here. I don't know why this is blacked out, but I'm just linearizing the values 0 to 1,000. You see the min and max are 0 and 1,000. From 0 to 4095. So we're going to display again the analog input value on the HMI. So we want to go online with it one more time and just see it working. And again, I'm connected to the EXRC1. Okay, let me see our voltage here, and again, if I disconnect, we should see everything turn off. And I plug it back up, and we'll get our states and our analog input back. Okay, so this is the UniCAN protocol in a nutshell. What we saw here is our tools for sending messages. Again, each controller can send a message to any other controller on the network. We saw our receive message. We can have an indication of any controller having sent to us. We saw our check alive. We can check to make sure that the controllers are available. And we use the struct to build and to extract a vector of mixed data. So that struct command as well, not limited to the UniCAN protocol. We can use it in Modbus or any other communication we'd like. Okay, so that is those are the examples, and that is the information for this webinar. If there are any other questions, we can leave this open for a little bit, and you can let us know, and we can answer them for you. Thank you, everyone, for attending. And a recording of this, and also the programs we used, will be available on our webinars page after. So again, thank you. Thank Jason for answering the questions.